So students, this is a follow-up example to the previous example that I've done, and you'll see that the spectra look fairly similar. I can just quickly show you the previous one that we carried out, and then you can compare it to this one. The one that we worked out in the previous video is this, and if you compare the two, you'll see that I have the aromatic ring here, I have a quartet, I have a triplet, and you'll see that this triplet is around about the same chemical shift. The aromatic peaks between here is slightly different, but more or less the same as the one that we've just done. And the only difference in the two spectra you'll see is this quartet. In the example that we've just done, it was at 4.2, but now I have this quartet at around 3. So that's the difference between the two. So you can expect the structures to look fairly similar. Well, I'll take you through the entire structural elucidation of this so we can get an idea of how to solve it. So I'll start again by looking at the molecular formula. The one given for this particular problem is C9, H10, and O. So fairly similar to what we've had previously. The other molecular formula was C9H10O2. So there was extra oxygen in the other molecule. This has one less oxygen. So I'll start again by looking at the aromatic region. It shows me that I have an aromatic ring, and there are 5 hydrogens on the aromatic ring, which indicates that there's just one substituent on there. I'll go to this aliphatic region now and see that I have a triplet and integrating to 3 protons in the methyl region of the spectrum, and therefore there's a methyl group here, and the fact that it's a triplet means it's next to a CH2. The only other peak I have is this, integrates to 2, so it's probably the CH2, and that CH2 is a quartet, which means it must be the next to the CH3. The only other CH3 I have is this one, so it means that the CH2 and CH3 is together to give us the quartet and the triplet. So fairly similar to what we said in the previous example. I get a quartet for the CH2. You see here I get a triplet for the CH3 next to a carbon with 2 protons. 2 plus 1 is 3. So I have fairly the same things. I take my molecular formula, C9H10O, subtract it from what I have, C6H5, plus another 2 carbons at C8H10. I subtract the 2, I get a carbon and an oxygen. And to link those two up, I can create a third fragment, which is the carbonyl group. I don't have any other oxygen in it like I had in the previous example. So with these 3 fragments, there's just one way to put them together, and that's to bridge these 2 groups by a carbonyl group, and I end up with that structure. If I analyze this structure, firstly look at the molecular formula, C9, 6, 7, 8, 9, H10, 5, 6, 7, 8, 9, 10, oxygen, oxygen, and this satisfies the molecular formula. The methyl group is a triplet, around 1, and I have that peak here. The CH2 is a quartet because it's next to a CH3 group. It's de-shielded by the carbonyl group, so I'm expecting something around 3 because that carbonyl group has, so normally a CH2 next to a carbonyl group, the aliphatic group on that side will be around 2.2, and this aromatic ring just adds to the de-shielding effect of this protons on the CH2 group. So you'll see that if I have an aromatic ring of the carbonyl group, that peaked normally around 2.2. If I just had the carbonyl, it shifted to around 3 because of the pi electrons here and the pi electrons of the carbonyl group. I get the CH2 proton shifting around 3. So this is related to the previous one. Look at the two together and you'll see the difference between the two is this particular peak here, and it just means that the CH2 now is directly bonded to the carbonyl group and not through an oxygen atom as you've seen previously.